Hi, my name is Nathaniel Frizzell. I'm an assistant professor at the University of Scranton, lead principal investigator of the Personal Space Weather Station project, leader and founder of the HamSCI community, and amateur radio station W2NAF. Today I'm going to talk about the HamSCI distributed array of small instruments Personal Space Weather Station, architecture and current status. This is a highly collaborative project, and I would like to acknowledge all of my co-authors and many others who have made this possible. What is a Personal Space Weather Station? The HamSCI Personal Space Weather Station, or PSWS, is a multi-instrument, ground-based device designed to observe space weather effects both as a single-point measurement and as part of a larger distributed network. It is personal because it is being designed such that an individual should be able to purchase one and operate it in their own backyard. In addition, the Personal Space Weather Station design takes into account the needs of professional researchers who might want to deploy these devices for their own specific purposes. The Personal Space Weather Station is being developed as a collaborative project under the Ham Radio Sciences and Investigation HamSCI Collective, led by the University of Scranton with collaborators at Case Western Reserve University, the New Jersey Institute of Technology, the University of Alabama, the MIT Haystack Observatory, TAPR, and volunteers from additional universities and the amateur radio community. What is the purpose of the Personal Space Weather Station? The Personal Space Weather Station aims to support two primary groups of users: space scientists and amateur radio operators. Each of these groups have different but related needs. As space science researchers, we want to observe, characterize, and understand ionospheric variability on small temporal and spatial scales. We want to understand coupling between the neutral atmosphere, ionosphere, and magnetosphere, and we want to validate and improve models with the goals of prediction and understanding. As amateur radio operators, we want to understand and predict radio propagation to support amateur radio communications, including public emergency service operations, contesting, and DX long-distance communications. We also want to study space weather and propagation for personal edification and to contribute back to science and the radio art. What makes up a Personal Space Weather Station? At the heart of the Personal Space Weather Station is a software-defined radio receiver with frequency coverage from approximately 100 kHz to 60 MHz. This frequency range was chosen because signals in the medium and high frequency bands, 300 kHz to 30 MHz, are particularly sensitive to variations of the ionospheric state. This receiver will be able to listen for signals of opportunity and transmissions made specifically for coordinated experiments. The primary output of the SDR will be raw in-phase quadrature IQ samples, which can then be derived into a variety of data products. This includes snapshots of the entire high-frequency radio spectrum, Doppler shift measurements of signals received from standard stations such as WWV and CHU, oblique ionograms from ionosons of opportunity, decodes of digital amateur radio signals including FT8, the weak signal propagation reporter whisper mode, and Morse code which can be sent to the reverse beacon network or RBN. These SDR observations can also be used to measure high-frequency band noise and detect lightning signatures. A dual-frequency Global Navigation Satellite System GNSS receiver chip will be used to serve as a highly stable frequency reference, providing precision timestamping with 10 to 100 nanosecond accuracy and provide total electron content TEC measurements. A magneto-inductive ground magnetometer will provide 3-axis magnetic field measurements at a 1-second cadence with about a 10 nanotesla resolution. A local computer will coordinate operation of all attached instruments, handle local data reduction, provide a local user interface or display, send data back to a central database, and receive commands and updates from the central control system. This system is modular, so instruments can be added or removed as needed. For instance, high-latitude users may want to add an auroral camera. Where will the Personal Space Weather Stations be deployed? Currently, the Personal Space Weather Station is funded on a DAISY Track 1 grant to develop prototypes rather than deploy a network. There is significant interest from the amateur radio community in this project, so we will be looking to encourage voluntary adoption of these devices by amateurs to create an ad hoc network. The amateur radio community is global, but is heavily weighted towards North America and Europe. Initial adoption will likely be in these regions. A number of amateurs at high latitudes, including Alaska, northern Canada, Norway, and Svalbard, have also expressed interest in this project. Low-cost and software-defined radio-based versions of the Personal Space Weather Station are being designed to help maximize adoption. To help maximize adoption, two versions of the Personal Space Weather Station are being developed: a highly flexible software-defined radio-based version and a more focused low-cost version. The software-defined radio-based version has the features that were already described: a synchronized dual-channel 0.1 to 60 MHz FPGA-based direct sampling software-defined radio, cross-polarized wideband received antennas, a dual-channel GNSS module for precision timestamping, frequency reference, and total electron content measurements. A more powerful single-board computer such as the Odroid N2 will be selected as the computer. The SDR in this version is known as the TangerineSDR and is being developed by TAPR, an amateur radio electrical engineering organization. The target cost of this system is about US $500. The low-cost version of the Personal Space Weather Station is being developed by Case Western Reserve University and the Case Amateur Radio Club W8EDU. The radio in this system is known as the Grape and has a target cost of about US $100. The Grape radio has a single channel and antenna and can measure frequency variations of received signals, such as those from high-frequency standard stations including WWV in Fort Collins, Colorado, and CHU in Ottawa, Canada. A single-frequency GNSS discipline oscillator is used as a frequency standard and for precision timestamping. An inexpensive Raspberry Pi will serve as the computer. Both the versions of the Personal Space Weather Station will use the same hardware for the ground magnetometer. Additionally, the SDR-based version will have a mode to emulate the low-cost version to allow uniform data collection across the maximum number of nodes for specified campaigns. I've already mentioned amateur radio many times, but what is it? Amateur radio, which is also known as ham radio, is a hobby for radio enthusiasts, including communicators, builders, and experimenters. The amateur radio community is comprised of a wide-reaching demographic, including all ages and walks of life. According to the American Radio Relay League, there are over 760,000 amateurs in the United States and about 3 million worldwide. Amateur radio operators are licensed by their respective federal governments through a testing process. This helps to ensure each participant has a basic knowledge of radio frequency and electrical engineering and a general interest in the subject. Once licensed, each amateur radio station receives a call sign such as W2NAF, AB4EJ, or W8EDU for on-the-air identification. This level of training and interest makes members of the amateur radio community ideal citizen scientists and engineers. Many people have already discovered that amateur radio provides a unique experimentation space for radio frequency science and technology with significant freedom to innovate, educate, and communicate. I want to note that while a license is needed to be an amateur radio operator, a license is not required to operate a personal space weather station, so that any interested person can participate. This is because a personal space weather station is receive only. To foster relationships between the professional research and amateur radio communities, I helped to found HamSCI, the Ham Radio Science Citizen Investigation. HamSCI is a collective that allows university researchers to collaborate with the amateur radio community in scientific investigations. HamSCI has the following objectives: 1. Advance scientific research and understanding through amateur radio activities. 2. Encourage the development of new technologies to support this research. And 3. Provide educational opportunities for the amateur community and the general public. HamSCI is a large citizen science community that is organized through email lists, regular telecons, and the annual HamSCI workshop. To learn more, visit hamsci.org/get-involved. How are we able to remote sense the ionosphere using amateur radio frequencies? If the conditions are right, radio signals of a particular frequency will be refracted back to Earth by the ionosphere. This is most common in the medium and high frequency bands, which range from 0.3 to 30 MHz. The red path on the ray trace diagram displayed here models the transionospheric link on 14.03 MHz between a transmitter in Florida and a receiver 1,700 kilometers away in Wisconsin. The ray trace is computed using the FarLap ray tracing toolkit through a solar eclipsed version of the SAMI-3 first principles ionospheric model. The ionosphere will modulate the radio signal as it passes through, and these modulations can be used to remote sense the ionospheric state. It is useful to examine radio signals across a wide range of frequencies because the ionospheric effects on radio waves, including refraction and absorption, are frequency dependent. Amateur radio operators have license to transmit on a large number of slice bands distributed throughout the radio spectrum, including those shown in the table on the right. A typical amateur radio station will transmit 100 watts or more into a dipole, vertical, or beam antenna. Common transmit modes include single sideband for voice, as well as data modes such as FT8, phase shift keying 31 Hz, weak signal propagation reporter, radio teletype, and Morse code. Recent advances in computing, the internet, and software-defined radio have led to the development of multiple networks for automatically observing amateur radio communications. These systems are developed and operated by volunteers in the amateur radio community. These networks include the Reverse Beacon Network, the Weak Signal Propagation Reporting Network, and PSK Reporter. Real-time and archival data are available to the public. These networks are quasi-global, and the data archives now cover an entire solar cycle. Already, we have been able to use observations from these systems in peer-reviewed scientific publications. As an example, the figure on the left shows observations and model results from the 2017 total solar eclipse published in Geophysical Research Letters. The top figure shows 14 MHz amateur radio reverse beacon network observations before, during, and after the eclipse. The bottom panel shows model results using far-lap ray tracing through the SAMI-3 solar eclipsed ionosphere. Both the observations and the model results show the drop-off in 14 MHz radio communications as a result of the eclipse-induced electron density depletion. The figure on the right also shows observations from the 2017 eclipse. These are unpublished carrier frequency measurements of the 10 MHz signal transmitted by WWV in Fort Collins, Colorado, and received by an amateur near Milwaukee, Wisconsin, using receiver with a GNSS disciplined oscillator reference. From 14 to 16 UT, positive excursions from 10 MHz are likely due to a shortening of the propagation path as ionospheric densities increase throughout the morning. Conversely, negative excursions in measured frequency are observed in the evening from 20 to 22 UT. Eclipse effects are observed between 16 and 20 UT, with negative excursions during the eclipse onset and positive excursions as the eclipse ends. The sudden jump in observed frequency just before 18 UT is associated with a C-class X-ray solar flare observed by the GOES spacecraft. Here, the figure on the left from a 2019 space weather publication shows two solar flare-induced radio blackouts observed over Europe on 4 high-frequency amateur radio bands. These data were collected by the Reverse Beacon Network and WhisperNet. Radio blackouts are typically attributed to collisional absorption due to a sudden increase in D-region ionization caused by a solar flare. On the top right, large-scale traveling ionospheric disturbances are observed in the RBN and WHISPER data, as the skip distance edge can be seen to oscillate between about 1,000 and 1,300 kilometers with a periodicity of approximately 70 minutes. These waves were also observed in differential GNSS total electron content data, shown in the lower right. While the observations shown so far are compelling, the amateur radio networks currently deployed were not designed with scientific use in mind. This is one of the motivations for the development of the Personal Space Weather Station project. The Personal Space Weather Station project is highly collaborative with multiple institutions and organizations participating. The project falls under the HamSCI collective and receives funding from the National Science Foundation. The University of Scranton is the lead institution for both HamSCI and the Personal Space Weather Station, and is responsible for overall project integration in radio science. TAPR, a volunteer amateur radio electrical engineering organization, and Zephyr Engineering Incorporated are responsible for the TangerineSDR, data engine, and magnetometer engineering. Case Western Reserve University and the Case Amateur Radio Club, W8EDU, lead the development of the low-cost Personal Space Weather Station. The New Jersey Institute of Technology is providing scientific oversight of the ground magnetometer. The University of Alabama is responsible for system software and database design, and the MIT Haystack Observatory is serving as a science collaborator. In addition, the open nature of the development process used has allowed many other institutions and people to collaborate and contribute. I'm now going to give a brief update on the status of each team and the specifications of their respective projects. The Personal Space Weather Station control software and database is being developed by the University of Alabama. The primary objective is to create local control software for the TangerineSDR, a central control system for the Personal Space Weather Station network, and a central database to collect observations. Currently, A prototype of the local control software exists and runs on an Odroid N2 single-board computer. This system uses data from a TangerineSDR simulator, can monitor up to 16 band segments at a time, and 4 types of data collection are implemented. 1. The snapshotter mode provides wideband high-frequency spectrograms at a 1-second cadence. 2. The ring buffer mode provides continuous local storage of IQ samples for up to 24 hours, and then uploads on request from central control. 3. The fire hose mode provides continuous transfer of IQ samples to a local computer. And 4. Propagation monitoring allows for decoding of FT8 and Whisper amateur radio digital modes on up to 8 bands at a 1-minute cadence. The scientific software-defined radio is being developed as the TangerineSDR by Tapper. It consists of a data engine, a radio frequency or RF module, and a timing module. The data engine includes a 50,000 logic element FPGA, 512 megabytes of RAM, gigabit Ethernet, and can support up to 2 terabytes on a micro SD card. The data engine will be able to simultaneously support 2 separate RF modules. The RF receive module features dual synchronized 14-bit 122.88 megasample per second analog to digital converters with dual SMA antenna connectors as input. It includes remotely switchable attenuation, a 20 dB low noise amplifier, a fixed 55 MHz low pass filter, an onboard 50 ohm calibration noise source, and a place for an optional user-defined plug-in filter. The GNSS timing module will be dual frequency to provide precision timestamping with 10 to 100 nanosecond accuracy and a frequency reference accurate to parts in 10 to the 13th over 24 hours. Currently, prototypes are expected by fall 2020. More information is available at TangerineSDR.com. The ground magnetometer module is being developed by Tapper and NJIT. Its purpose is to establish a densely spaced magnetic field sensor network to observe the Earth's magnetic field variations in 3 vector components. The target performance level is about 10 nanotesla field resolution with a 1-second cadence. The magneto-inductive PNI RM3100 magnetometer module will be used. The magnetometer module will also include a temperature sensor. Prototypes have been made and software development is underway. Testing is planned at established quiet sites with co-located research-grade magnetometers, such as at the Jenny Jump Observatory in Hope, New Jersey. The low-cost personal space weather station is being developed as a GRAPE receiver by Case Western Reserve University and the Case Amateur Radio Club W8EDU. Its primary objective is to measure Doppler shift of HF standard stations such as WWV and CHU. The cost target is about $100. There are 4 stations currently deployed, some with prototype receivers and some with ham transceivers. Preparations are also underway to set up stations with several aspiring data collectors. Doppler shift data is collected via spectrographs and frequency estimation algorithms. The low-cost personal space weather station team is currently fine-tuning metadata formats and automatic data upload. In summary, HamSCI is a collective that aims to bring together the amateur radio and professional space science research communities for mutual benefit. Peer-reviewed studies of ionospheric effects generated by solar flares, solar eclipses, and geomagnetic storms using data from propagation observation networks created and run by the amateur radio community have already been published. In an effort to improve the scientific usability of amateur radio observations, HamSCI is developing a personal space weather station designed with science requirements in mind from the very beginning. These modular systems will include high-frequency radio receivers for studying the ionosphere using signals of opportunity, ground magnetometers with approximately 10 nanotesla resolution, GNSS receivers for precision timestamping and frequency stability, and a target price between $100 and $1,000 depending on capabilities. Finally, I would like to acknowledge support from the National Science Foundation, the amateur radio community, my science and engineering collaborators, and the many other people who have helped to make this project possible. Thank you very much for listening to this presentation. I hope you enjoyed it.